Hello, everybody. Welcome back to Chem 121. Not many of these lectures left, because we are almost done. Before we start on the lecture tonight for the lab, and then we have a little bit of Chapter 9 and 10 to do afterward, just a brief update on what's upcoming. So there is a quiz due tomorrow. That's quiz 8. After tonight, I will post quiz 9. There won't be a quiz 10 like I mentioned yesterday. That'll just get rolled into exam 2 in the final, whatever we cover. Chapter 9's quiz will be due sometime next week. The lab that we're talking about tonight will be due on the day of the final, so be very mindful of deadlines coming up. Just like before, I will do the last call thing, so, if you can't get it in on the day of the final because you just have too much stuff going on, that's fine. As long as you get it in within a day or so, that should be okay of the due date. So, if you turn it in on Friday before I call last call, then that's fine. It marks it as late. I ignore it. It doesn't matter. But I do want to go over... Oh, I got to capture the window. Hold on. Is this the one I want? Yeah, that's the one I want. I do want to go over the lab worksheet a little bit really quickly, just so that you have that handy. I don't know why this is actually on top, so let me... I don't really need all of this, so I can make it bigger. There we go. Very professional stream here, don't mind me. Alright. So the lab worksheet number 5, it is now available. You should be able to see it. I opened it up this morning. I forgot to do it last night. But lab number 5 is basically a bunch of videos talking about solubility. And it looks scary. There's all these organic molecules. Ah, look at all these pictures. The diagram teaches you how to read these structures, but I do want to go over very briefly how to read organic structures so that you don't just look at this and try and interpret it and go, I don't know what it's trying to tell me. So we have something handy here. I don't really need this window, so let me just get rid of it. Boop. Let's talk about how you read an organic structure. So, in organic chemistry, people have to draw really big molecules all the time. And so something like this. If this was the Lewis structure that I wanted to draw, you can see how tedious it is to put all these H's in here. So whatever this is, I don't know what this molecule is. It's some sort of carboxylic acid. But what we can do instead is we can say that each of these carbons here that I'm indicating with these purple arrows, we're going to turn carbons into points. And by a point, what I mean is like a little dot, like I just drew right here. And then I'm going to connect those points with bonds. So I have 1, 2, 3, 4, 5, 6 carbons. I guess I could number them here. I have 6 carbons here. So what I'm going to do is I'm going to make 6 points. And I'm going to connect them in a sort of zigzaggy way. And then the end structure looks like this. 1, 2, 3, 4, 5, 6. That actually looks really sloppy. Let me redo that. What I should have just done was draw the zigzag. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And so I'll put the numbers in here too so that you can have a direct analog to follow here. So we turn the C's into points to make this sort of like zigzaggy line that you see. The other thing that we do is that H's are what we say implied. And so implied means that any space that looks like it doesn't have an octet, so like this carbon that I'm circling right now with my pen, right here, I only have one thing bonded to it, but that's not going to satisfy the octet rule. There should be 3 other things coming off of that. That's these 3 H's up here. Anytime that I don't draw something in my organic structure, it's assumed to be H's. So even though there's supposed to be H's coming out of here, I'm not going to draw them. They're implied. So whenever you see an end carbon right here, there's going to be 3 H's coming off of it. This second carbon right here, there's going to be 2 H's coming off of it. This one also 2, and so on and so forth. Anything that is not C or H is drawn. So I have this double bond O, so I'm going to go double bond O, single bond O. And then because the H is connected to an O and not a C, I am just going to draw that H in, but usually what people do is they omit the bond and make that assumed too. Sometimes people will draw in the electrons, sometimes they won't. The electrons are also implied, so these dots appear and these dots on this oxygen. Those are implied. They still exist. They're just not drawn in the structure in order to make something that you can quickly draw. So, like, I can really quickly draw any sort of crazy molecule that I want to. Just drawing organic structure. Whereas if I was going to draw that in traditional structure, this should be connected, by the way. I have to go CH3, CH2, CH, CH, CH3, CH. And I'd have to draw all of that. And that'd be really tedious for me to draw if I was working with these molecules all the time. And also, if you're trying to print it in a textbook, the amount of ink that you have to use goes up exponentially as the molecules get more complicated. So people have settled on this as a compromise. Like, this is the new language that we're going to develop for talking about organic structures. Organic, by the way, when I say organic, I mean structures that primarily contain carbon and hydrogen. Organic structures are very prevalent in 131, and they're also really prevalent in any activity that involves talking about polar versus nonpolar, which is actually what solubility is. So we're going to use organic structures in this, not just to get you used to it, but because it's just simpler. Because I can't draw this fatty acid that's shown here. Like, if I drew that with C's, it wouldn't fit on the paper. So you can see what's going on here. This is just a long chain of C's and H's. There's a C here with double bond O bonded to this part. This part has actually been drawn in with C's just to point out what it is. You could just draw it like this down here, which is what eventually happens. So a bunch of these molecules in this documentation are going to be drawn in this shorthand. So that's what it's trying to do. And what this worksheet is going to have you do is compare different structures and their solubility based on a bunch of videos I found on YouTube. So you're going to look at temperature. You're going to look at solubility of ionization. You're going to look at, this is more ionization basically. And then you're going to look at different molecules and how soluble they are. So I have a video that shows all of these things mixed with water. And we're going to see how well these mix together with water by adding food coloring to it. Though food coloring dissolves in the water, and anything else that dissolves in the water will also turn blue. But if it doesn't dissolve in the water, it doesn't turn blue. And then finally, I have a video talking about iodine. So iodine, as a molecule, you should be able to draw its Lewis structure to tell me if it's polar or nonpolar. You should be able to tell me if hexane, water, or dichloromethane are polar or nonpolar. And then write generalizations based on that, and then answer a few questions afterward. All right. So that's the experiment. It's basically going to be watch a lot of videos. I mean, surprise, surprise. I can't make you do this in class, unfortunately. Normally what we would do is I just give you a bunch of test tubes and a bunch of chemicals, and you mix them together and see what happens. But solubility is very important, especially in medicine, because you don't want to be giving patients medications that are insoluble. And so knowing that, like, hey, this might be insoluble, maybe I shouldn't do this, is a good bit of knowledge to have. You don't want to clog the line, as I think that I have a nurse friend, and I believe I've heard her talk about that. If you make an insoluble salt in the IV, that's really, really, really bad. Yeah, that's the lab. There is a worksheet that you have access to as well. It's a little clipped on the video, but it is only 2 tabs this time. Lots of these are just like the questions from the videos, and then there's the analysis stuff where you gotta tell me soluble or insoluble, and then explain your answer. Make sure you're explaining your answers. Don't just say soluble or insoluble. Even if you're saying the same thing over and over and over again, that's totally okay. That's kind of the point. All right. That is all available on the modules tab. That should look like this now. Here's the videos. I believe that this will link to... This should be public. Yeah, it's public. Okay, so everybody can see this. And yeah, there you go. That'll be due on the day of the final next week. Sad face, I know, because we're almost done. Okay, so let me get rid of this. Where? Oh, I'm in the wrong thing. There we go. If you have questions about anything for the Q&A, you can ask them as we go. Otherwise, I'm just going to continue with the lecture. Let me get rid of this window in my screen here. We're going to finish Chapter 9 today. We're going to start Chapter 10. There's a lot in Chapter 10 that we don't really cover, just because usually we run out of time, so I'm just going to do what I normally do. And whenever we finish the content, then hooray, we did it. You've completed Chem 121. That's coming up a lot sooner than you think, because Chapter 10 is the last chapter. So, congratulations, you've almost made it to the end. We're going to talk about a principle today that involves how equilibrium changes when you do stuff to it. And principally speaking, and I'm not using the word principle because it's on my screen, equilibrium in biological systems is not really something you want to attain, because that would mean that you would die. If your body reaches equilibrium, that's because the reactions that keep life going have stopped producing the things that you need for life. So we need to drive equilibrium forward and keep the reaction going. And the way that you do this is, well, you need energy. That's ATP. You get that from things like glucose. As you run out of glucose and turn it all into ATP, you don't want it to suddenly start turning back into glucose. So what do? You get hungry. You get a craving for things that have glucose. So you eat. That changes the equilibrium. And how does it change? That's important to understand. And so this is Le Chatelier's principle. Chatelier's principle basically says, if you have equilibrium and you then change it so that the system's not at equilibrium anymore, like say I have this reaction, I have A plus B makes AB, and then I suddenly flood my container with B, like I pour extra B in, is the system at equilibrium anymore? Well, if you remember yesterday, we were talking about equilibrium constants. And so this has some equilibrium constant K. And we said that K is the ratio of products to reactants. Which in other words would be, I've got AB, and I've got A and B. Now let's suppose that I make B much larger by filling the container with B. Does this equal K anymore? What do you think? Type in the chat. Does it equal K anymore if I change the number for B? Yes or no? This is really my test to see if anybody's here, although I can actually look that up. Yeah, there are people here. I always wonder at the start, because nobody says hi or anything. You used to say hi. Oh, there's the answer. Cool. So yes, why do you think it does equal K? Because this would be for some amount that I have when the reaction's at equilibrium. But then if I add more to it, does this value equal the same number? It's not the same number. That's right. Let's show that mathematically. So let me erase everything. So I'm going to show you how to calculate K, even though I'm not going to test you on this. So let's suppose that I had, I don't know, this was the concentration of each of these things. And I said calculate K. Well, K would be AB over A times B. So K for this reaction would be 2, if this is what we got. Now, let's suppose that I changed this number. I made it bigger. Does this still equal 2? And you should be able to say, well, no, now instead of dividing by 1, I'm dividing by 5. It'd be whatever 2 divided by 5 is, like 0.4 or something. So by changing one of these numbers, I change the value of K. But that's not what's supposed to happen, right? K is supposed to be a constant if the system's at equilibrium. So in other words, by adding more stuff, the system is not at equilibrium. Anymore. If the reaction's at equilibrium and you add something to it or take something away, it's now no longer at equilibrium and something will happen. What exactly will happen? Well, that's what we're going to talk about. So if you add more of something, and in this case I picked B, the equilibrium constant value would change. But if it's a constant, it needs to always be that number. So what the reaction will do is it will change all of the values of what's in there so that it can get back to that number. Now, without calculating numbers, it's hard to prove that quantitatively. We'll have to sort of just take it on faith. But a reaction will try and undo the change that you did. And so this is known as Lachelier's principle. If you change the value of K, the reaction will react further so that it goes back to the original value of K. Now we're going to do this with a sort of like seesaw sort of illustration that I'm going to try and draw on the thing here. Let me do that. So let's get a reaction on the board here and show this on the... Oops, that's the wrong one. There we go. Let's put this back up here. Alright, so I'll put this in the middle here. And so what we're going to do is I'm going to make like a little seesaw here. And so I have A plus B and AB. And my reaction is at equilibrium. But let's suppose that I add more B. Let me just do this. I'm going to add a bunch of B to this mixture. We're going to see if this actually works how I intend it to. Alright. If I add way too much to this side of the seesaw, what would happen is the seesaw would do this. That almost worked, except I didn't imagine that I would go off the screen. So we'll have to deal with that. Alright. So what's happening here is that if I add extra B to the mixture, I am no longer at equilibrium. I have too much B. So what I have to do is I have to go back to equilibrium. So, oops, that's the wrong command. So I gotta change this back to 4. To go back to equilibrium, in order to go back to equilibrium, I had to use up some of that B that I added. So we have to do that. So that's our first thing. But B reacts with A, which means that we have to also use up A. And when A and B react, they make AB. So we also make AB. So if I use up B, this number will decrease. By using up B, I also use up A, so this number will also decrease. But by creating AB, this number will also increase. And as a result, what will happen is that as I make more AB, this side will then get heavier, and this side will get lighter. And the end result is that it will try to go back to equilibrium. And I don't know how I'm going to be able to do this now that I could do it this way, I guess. Now the reaction will go back to equilibrium. And part of my AB got chopped off because it didn't retain any pixels that went off the screen. So if I add something to the mixture, it will no longer be at equilibrium. Boop. Oh, I don't have a history, so I can't actually do that. I can do this, though. So if I have something that I added, it will no longer be at equilibrium. What the reaction will try and do is it will try and undo what I did to get back to equilibrium. All right, let's do another example here. So let me clear everything. Oh, I got to do this. And then I'm going to go like that so that I have more space to work with. Okay. So let's draw another seesaw. That's not the pen, that's the select cursor. And now this time what I'm going to do is I'm going to add AB to disrupt equilibrium. So that means that I am going to put a bunch of this in here. That's probably overkill. That's fine, I guess. And now that I've added AB to the reaction mixture, the system is no longer at equilibrium. So which way is this going to tilt based on me ruining equilibrium? Is it going to tilt towards the reactants or towards the products? So which way will it tilt? Good, it's going to tilt towards products. So there's our equilibrium right now. All right, I guess I do have to apply that. All right. Now that the reaction is in this situation, how does it get back to equilibrium? What will the products turn into? Because I have too many products now. It's not at equilibrium. Ow. I hit the wrong button. So we'll fill in the blanks there. To get back to equilibrium, what do I have to do? I have to turn something into something else. What is that? Well, if I use a B and A, what will I create? So if I use up A and B, and I make more AB, then the AB side goes like this, right? Am I getting back to equilibrium by using up A and B? I gotta level them back out, right? So what should I do instead? Oh, that's not what I meant to do. Because the left side, I have too few. That's why it's up in the air like this. And the right side, I have too much. Oh, I didn't mean to move it. Put it back. What if instead of using A and B to make more AB, I instead did the reverse reaction? Yeah, there you go. I could break AB into A and B. So if I used up this stuff right here, this side would become less, and this side would become more. And that would turn my reaction back to equilibrium. And when that happens, then I would have less AB. I'm trying to erase this to make it look like there's less of it, but it's actually really hard to do. And I would make more A plus B. So to go back to equilibrium, I would turn my AB into the reactants A plus B. Or in other words, I would turn products into reactants. So in other words, if I add a product, I will turn my products back into reactants to undo what I did. That's what the reaction tries to do. If I add a reactant, the reaction will try and turn those reactants into products. Now, I'm not increasing AB. I only added A. I'm not increasing A plus B. I only added AB. The reaction itself, though, would then break AB apart into A plus B to undo what I did. Another way that you could think of this is, so let's see here. And we'll get a little vulgar here, I guess. So let's consider this reaction. Which you can't see because it scrolled off the thing here. So you turn food into... I don't know if I'm going to be able to use this as an analogy. I might laugh too much. So you turn food into waste products or energy. Maybe I should use energy instead. Let's not go for the toilet humor. So we'll put those on the balance here. All right. Now let's suppose that you are very hungry and tired. In other words, you just don't have the energy to deal with my bullshit tonight. So you don't have any energy. I'm so light on energy. What you would have to do is you would have to gain energy somehow, right? In order to gain energy, we would have to convert food to energy to get that back. So what that means is that you would eat. If you don't have enough energy, you would put in food. All right. Let me get another problem on the board that has actual chemicals in here. Oh, what did I do? Hold on. I ruined everything on my screen here. That's not select all. There we go. All right. So the overall trend here is that if you add something, your body will use it up. So in the food analogy, if I ate too much food, compared to me not having eaten any food at all, my body would then use up the food to turn it into energy, and I would gain energy. Now, you can also do the same thing if you remove stuff. If you have a hole in the reaction, like say I removed all of the A, then the reaction would try and replace it. So here's an actual reaction. Let's consider this, and we'll do each of these steps here. So let's suppose that I have some amount of N2, H2, and NH3, and it's all in a container, and I have it all there, and I can push a button that says add ammonia, which is NH3. So let's go back to this, which shouldn't be there. I erased it. There we go. There. All right. I'm a little off here. I want to try and line this up with the picture at the top there. Okay. So we got N2 plus 3H2, and we got NH3. All right. So I'm going to add NH3 to the reaction mixture. I forgot my fulcrum here, so I'll just do that. If I add NH3 to the mixture, then the reaction is no longer at equilibrium. And so I break the equilibrium. I'm in the wrong menu. There we go. If I break the equilibrium, this happens. Boop. I gotta get back to equilibrium, so I need to go... That didn't work. There we go. I need the reaction to go in this direction to turn this stuff back into this stuff in order to get it to go backward. Actually, let's not do that part yet. So let's see. So I added NH3 to break equilibrium. So the black writing is what I did to the reaction. The purple writing is what the reaction is going to do. So the reaction breaks NH3 into N2 and H2. And by doing that, I use up the added equilibrium, so it's no longer there. And I create more of this stuff so that the reaction will then tilt back in the direction that I want it to. Oops, dropped my pen. There we go. All right, that was number 1. Let's do number 2. What would happen if I instead removed N2? So let's clear this part. We'll clear this part. So now what we're going to do is I'm going to disrupt equilibrium by adding... It's not adding, I'm sorry. We're going to remove something, aren't we? I'm going to remove the N2 from the reaction, which means I'm going to do this. Since I removed this side is no longer at equilibrium. This side's too light. There are too few reactants. And so what's going to happen now is that since there's less stuff on that side, it'll do this again. which direction will the reaction shift? Will it shift towards reactants to make more reactants, or will it shift towards products to make more products? Remember, I got rid of N2. There's now not very much of it in the system. I got to get back to equilibrium. So what should I do? Which direction do I move? Towards products or towards reactants? Good, yeah, I would move towards reactants because, I mean, if there aren't any there, I can't use them up, right? Now, I didn't use all of them, but if on the assumption that I did, I would have to turn some of this, the ammonia, back into this stuff to get it back to normal. So, what does the reaction do? It does nothing because I need to select all. The reaction breaks ammonia into N2 and H2 to fill the gap. So if I made a gap by crossing something out, I'm going to have to turn stuff into the thing that is missing in order to restore equilibrium. Oops. All right. And so I could do this all day. I could say, what if I added N2? Well, if I add N2 to the reaction mixture, I have too much of this stuff, then it will shift in this direction to use it up. What if I add H2? Well, I have too much H2, so it'll shift in the direction of the products to use it up. What if I remove ammonia? Then I have too little ammonia. I need to shift in the direction of the products to create it. So whatever I do, the reaction responds by trying to undo the change. That's what it's trying to do. It's trying to get back to equilibrium. Now, adding and removing stuff are not the only ways that we can change equilibrium. Equilibrium constants are linked to temperature, and they're also related to the amount of stuff in terms of pressure. So all of the stuff in this reaction was gaseous. So if I go to the next page here, and we look at this reaction, if this was in a container like this, these numbers tell me how many particles there are available. And the number of particles is related to pressure, because you remember the gas law. PV equals nRT. If N goes up, P must go up. In my container, let's suppose that I have this amount of each substance. I messed up there here. If my reaction is at equilibrium, there will be some pressure. And the reaction wants to stay at that pressure, because pressure is related to the amount of things that are in there. If I had 2 moles of N2, I would have more pressure. If I had 0.01 moles of N2, I would have less pressure. And so that would affect how the reaction works and what its equilibrium would be. Now let's suppose that I do this to it. I'm going to take my container and I am going to make it much smaller. If I decrease the volume of this, what would happen to the pressure? What happens if V goes down? What happens to P? We got to remember that from chapter 7. If V decreases, then P does what? P increases. Very good. But if P increases, I'm no longer at the original pressure P in the box. And so I need to get back to this if I want to be at equilibrium. But if it's not the same, I need to change it such that it is the same. So what the reaction will do is it will try and reduce the pressure by reducing the amount of stuff that's in there. And the way that it does that is that the reaction will move in the direction with the smaller number of moles. How many moles of reactants are there? Well, there's 1 plus 3 moles, so there would be 4 moles of reactants. How many moles of products are there? There's 2. Something with 4 moles would have a higher pressure than 2 moles because there's just more particles hitting the container. So in order to reduce the pressure to undo this increase that I put on it because I decreased the volume, the reaction will shift to the side that has fewer moles. That's this. So if I decrease the volume in this case, the reaction will shift towards products. So we did a bunch of stuff in this problem. So let's write this out. Let's color code it again. So the first thing I did was I reduced the volume of the reaction. What was the consequence of that? And the consequence was that P increased because the volume decreased. So far, so good. To undo this pressure change, the pressure needs to decrease back to what it was at equilibrium. So, in order to do that, the reaction moves to the side with fewer moles. All right, let's suppose I did the opposite. So let's get rid of all these actions here. And I'll just pick a new color to indicate what I've changed here. That's the wrong pen. There we go. All right, let's suppose that I expand the container. I make it really big. If I increase the volume, what would happen to the pressure? If volume goes up, the pressure inside the container goes down. Good. Okay, now the pressure is too low. It needs to increase to go back to equilibrium. So, which direction should my reaction move? If I want pressure to increase, should I make more stuff or less stuff? Oh, I made a happy face there on accident. So since I want the pressure to increase, because it decreased from what I did, the reaction needs to move to the side with more stuff. Okay, so that's the takeaway. If you change the reaction such that the pressure goes down, the reaction will respond by alleviating the pressure. The pressure will shift the reaction in the direction that has fewer moles. If I decrease the pressure, the reaction will try to fill that gap. It will try to increase the pressure to undo what I did, so it will move to the side with more moles. Pressure is kind of weird. You have to consider how the pressure affects the reaction by looking at what the reaction is telling you. If I have more moles on one side than the other, pressure will affect it. What if I had a reaction where the pressure had this, or the number of moles on both sides was the same? So like I had 2 and 2. If that was the case, then pressure wouldn't do anything. I could pressurize it all I want, or I could expand the volume all I want. It doesn't shift in any direction because the number of moles is the same. It wouldn't fix the problem, so it just lives with it. Alright, I gotta clear the screen. I don't know where my cursor is. There it is. And there's our summary. If pressure increases, the reaction moves to the side with fewer moles. If pressure decreases, the reaction moves to the side with greater moles. The reason for that is it's trying to undo the pressure changes that we are inducing. Now, increasing and decreasing pressure is difficult, but changing the volume is not. If I had like a piston, I could just squeeze the ends of it together, or I could pull the piston out and expand it. That's pretty trivial to do. So most of these questions will involve you manipulating something with relation to a volume. And then you have to use the gas laws to figure out, oh, well, volume increased, so pressure went down. All right. So let's do another example with this, but I'm going to use a different reaction because we already talked this one to death. So let's go to this. We'll put this up here, and I'm going to pick a different reaction. So let's see here. I'm just going to make something up. So A plus 2B makes C plus D. All right. So first, let's count the number of moles on both sides. How many moles of reactants are there, and how many moles of products are there? Type it in the chat when you've got your answer. Good, so there are 3 moles of reactants and 2 moles of products. All right, if the volume for this reaction increases, then what will happen to the container? Well, V goes up, P will go down. And if P goes down, I got to fix it. How do I fix it? Well, the reaction will shift in which way? Reactants or products? So if the volume increases, the pressure decreases. I have to fix that. I got to make more pressure, so I shift towards reactants because that is the side with more moles. Good. All right, now what I'm going to do is I'm going to clear this part. Boop. And then I'm going to do this. Ready? Whee! So now this number is 2. And this number is 3. And now we're going to ask the same question. If V increases in this situation, do I still go towards reactants or products or what? Where do I go? Well, if V increases, P still decreases, so that hasn't changed. And the reaction moves to the products because it's the side that has more moles. There you go. Very good. So, even though I did the same action, in this case I made more products. Because expanding the container reduced the pressure. I have to fill in that pressure. I have to move towards the side that has more moles to fill in that pressure. All right. That's the effect of pressure. And so these examples right here are more or less what we just did with the ammonia. If I increase the volume of the vessel, the pressure goes down, so I need to move in the direction that has more moles to fill in that gap of pressure. In this ammonia example, that would be the reactants. If I reduce the volume of the vessel, the pressure increases. I need to undo that increased pressure. I would move the reaction in the direction of fewer moles, which ends up being the products here. So it is relative to whatever reaction you do. So you have to be mindful of that when you're answering these questions. Look at the reaction first and look for those numbers if you see a question that involves pressure. All right. The last thing that we can talk about is how heat works. Heat works just like a reactant or a product, because remember, if we have a reaction, we could just put the word heat in there. So here's a sample reaction that I have. If I add this blue thing, and I've color-coded these so that you see what color they are, because we're going to see a video about it in a second here. If I add this blue thing to water, what ends up happening is it turns pink. I make this, and it gets hot. So first of all, let's label this reaction. Is this reaction exothermic, or is it endothermic? Where's the energy going? Is it going into the reaction or out of the reaction? Endo or exo? You can remember which one's which by remembering endo, which is like enter, and exo, which is like exit. It's all Latin and Greek things. I'm not a linguist. Good, this is exothermic, because the energy's coming out. It's a product, right? Okay. Now let's suppose that I put this reaction in a boiling water bath. In other words, I expose it to large amounts of heat. If I put extra heat into the reaction, the amount of heat that I have is too big. If I have too much heat, which direction will the reaction shift to use up the heat? Will it shift towards reactants or products? So again, think of it as if I have heat is actually like a substance, like a physical thing. And I'm going to throw tons of heat in the reaction vessel. Which direction would it move? Now, if it moves towards products, I would create more of these things, of which heat is one of them. So that can't happen, because then I would just have even more heat. How do I get rid of the extra heat that I added? I would have to turn heat and HCl and the pink thing into water and the blue thing. So if I add excess heat to the reaction, then what happens is the reaction uses the heat to form more reactants. And so the reaction would shift towards the left, towards reactants. Now, what would happen if I put it in a cold bath instead? If instead of putting it in hot water, I put it in cold water. And so now there is a lot less heat. Keep in mind, these arrows are just showing how the amounts are affected and not like the direction of the seesaw, if you're thinking of the seesaw example from before. If I have too little heat in the reaction will try and replace it because I took it away. Which direction will the reaction shift? Towards reactants or products? Got to make more heat to replace what I lost. Any idea? It would move towards products. Good. And the reason for that is because... Let me erase all here. So if I remove the heat... say in a cold bath or an ice bath, then the reaction tries to replace the lost heat by shifting towards products. Now, because I've drawn these colors on here, you can actually use this as a visual guide to see what's happening. And I actually have a video of that right here. So what we're going to do is, first I got to get rid of this text that's overlaying it so you can see it. We're going to go to this screen here. I'm going to put this at the top so you can see it. Oops, that's too big. And then I'm going to click on the link once I have my cursor. And now I should be able to capture this. That's the chat window. I messed up. Hold on. I ruined everything. Is this what I want for that window? Yeah, okay. I want this one, which is that one. Alright, hold on. I gotta make it bigger. Alright, so what we're going to do is we're going to take the reaction that's at the top of your screen there. Let me move it over so it's not overlapping the chat. And we're going to subject it to different conditions. And what I want you to try and do in the chat is predict what's going to happen here. So here are the two colors. The one on the left is the water cobalt mixture. The one on the right is the chloride cobalt mixture. And don't worry about the equations that pop up because it's just what I have on the screen. All right. So what I'm going to do is I'm going to take my pink mixture and I'm going to add HCl to it. If I were to add HCl, what would happen to the color? Would it become more pink because I made more of the pink stuff? Or would the pink stuff turn into blue stuff and then the reaction would turn blue? Remember, I am adding HCl. So look at the reaction at the top. If I add HCl, which direction will the reaction shift? You can say either towards blue or towards pink or towards reactants or product, whatever you want to say. Let's get a few guesses in here, and then we'll see if you're right. I'm just going to do this so that I know what are the old responses. There we go. So keep typing in some guesses here. We can get a few people to predict. Remember, I'm adding HCl. I'm not trying to psych you out either. I just was hoping more than one person would guess. Alright. Well, these people who want participation. Hooray. Alright, let's see if you're right. That's not the, that's the chat. I didn't have that on the video. So we're going to add HCl to this. Boop. Alright, what's happening to it? You'll notice it says Cl minus. It doesn't matter. It's HCl. It's the same thing. What happened to it? What color did it turn? I don't like the equation on the screen. I just want to see the blue. There we go. So it turned blue, so it must have turned into more reactants. So the reaction did shift towards reactants. So both of you were right. Very good. All right, let's do another one. And he's just going to mix it up a little bit. All right, now we're going to add water to it. If I add water to both solutions, I'm only going to add it to one, but if I were to add it to both solutions, which direction would the equilibrium shift? Would it shift towards reactants or products? Good, it would shift towards products because too much water, gotta get rid of it, gotta use it up. Turn it into products. Let's see if you're right. The water reaction takes a second for some reason. And now when we mix it, it is once again pink. Alright. We're going to do a different experiment here now. I'm going to add HCl to turn it blue. And then we'll mix it really quickly. And we've already seen this one. But now what I'm going to do is I'm going to add silver to it. What the heck? Silver doesn't even show up in the reaction. How does this do anything? Well, here's a thing that you might remember from Chapter 8. Silver plus Cl makes an insoluble solid. So in other words, adding the silver removes HCl. If I remove HCl, which direction will the reaction shift towards? Products or reactants? Which color should it turn when I remove HCl by adding silver? And I'll just do this again so that it lines up properly in the video. What could it do? Removing HCl will turn the solution pink. Very good. Now it turns pink because if I don't have HCl, I got to replace it, right? So the amount of HCl that I have left over... Oops, I got to go to this window. So if I don't have enough HCl here, I need to replace it, which means I got to turn these things into HCl and this. So the solution should become more pink. Let's see if that's what happens. Now the white solid that you're seeing is silver chloride. And it's just white itself. But when you mix this up, what color do you notice the whole thing has turned? Let's turn pink, because we made more of the cobalt water thing. Alright. None of these are gases, so we can't show the effects of pressure. What we can show is the effects of temperature, because you can see the word heat on there. So let's do that. On the left is a container that has hot water, and on the right is a container that has ice water. If I put the solution into the hot beaker, what color will it turn? Blue or pink? Pink or blue? Maybe it'll turn some other color. No, it'll only be one of those two colors. Which color will it be, though? Pink or blue? I forgot to put my little divider. That's okay. So let's see what happens. We'll see if we can explain. So we put the tube into the hot water and, oh, it immediately turned blue. Uh-oh, what happened? Why did it turn blue? Remember, heat can be treated as a substance in the reaction. And up there we got heat on the product side. If I add heat, it's like I have too many products. And if I have too many products, I got to turn them into reactants, which makes it blue. Now, let's suppose that I put it in the cold bath. If it's in the cold bath, I'm losing heat. I get rid of the heat as a product. Then I have too few products. What color should this turn when I put it in the cold bath? What do you think? I hit pause, by the way, so... What color will it turn now when I put it in here? Will it turn more blue or will it turn to pink? Good. It will now turn pink because pink is on the product side, and I need to make more products to replace the heat that I lost. And it's really hard to see here because the video kind of abruptly cuts out at the end. Oh, I paused it too late. Hold on, let me go back a frame at a time. There you go. You can see that the pink is starting to appear at the bottom. And there you go. All right. Well, Chatelier's principle is one of those topics that needs a lot of practice. So what I want you to do is I'm going to put this on the screen really quickly. You guys have these questions on your slides, presumably. Go ahead and write these down if you'd like. And then during the break, think about what will happen with each of these. And then we'll go over them, because this is the end of the chapter. It's the last slide. So I'm going to leave that up there. I will put the timer on the screen here. Boop. Oh, I don't have the timer handy. There we go. We'll just put it on the screen here. That's not the timer. That's the timer. We'll put it... Oops. Oh, what have I moved? I don't know what I'm moving. There we go. We'll put it over here. I'll start the timer. We'll take a 10-minute break. I will turn the music on just so that I know, so you know when the break is over if you aren't paying attention. But earlier today, I stopped the timer on exactly 10 minutes, and everybody was super excited about it. So, we'll see if I can do it again. See you in a bit. Oh, it was pretty close, though. Don't mind me, I am eating Triscuits because I am hungry. Crunch, crunch, crunch. So let's go back to this problem here. Boop. Get rid of that. Hopefully everybody had an opportunity to look over this question. So let's talk about it. Let's see if we can figure out what happens. So if I add more H2S to this reaction, what will happen to the mixture? Will it become more red or less red? What do you think? Type your answer in the chat. Oh, goodness. Sorry about that. I clicked on the screen and it advanced the slide. So if I add more H2S, I have too many reactants. The reaction will turn them into products, of which one is red. So it will turn more red. Good. How about if I remove CH4? So here's my CH4. Oh, I took it away. Which direction will the reaction shift? Will it turn more or less red? Good, because I have to fill in the gap, which means I got to turn my CS2 back into CH4. So it turns less red. You guys got it. All right. What if I make the solution really cold? What does cold do to my heat? It means I'm removing it, right? So what will happen? Will it turn more or less red if I make it really cold? It should turn less red. Very good. All right, and then the last one. What happens if I reduce the volume of the container? I'm going to take the container and go, yeah, and I'm going to make it really small. If the volume gets smaller, the pressure gets bigger. Which direction will the reaction shift? I gotta find the right color pen here. So if the volume goes down, the pressure goes up. We need to make the pressure go back down. Which side has lower pressure? Products or reactants? We want to go to the side with the less moles, which is the reactant. So what color will it turn? It will turn less red. Very good. We'll write that there. There you go. This slide is pretty much what I have to do to give you a test question for this. All I can really do is post a question like this on Canvas, and then you just check more or less red. So when you get your Le Chatelier question, it'll be something very similar to this. Now all I have is like bits of Triscuit in my throat, and I'm like, I need water. All right, that's chapter 9. That's everything there is. I guess I'll turn up the sound so you can hear the hooray. Oh, it didn't even play. Hold on. There we go. I don't know why it stopped. I love Triscuits too. Triscuits are amazing. All right. Let's see here. So I gotta do this really quickly. And I gotta move the chat so I can get chapter 10 here. Let's see here. We're gonna do just a little bit of acid-base chemistry today. We're not gonna do all that much. I just want to introduce you to what acids and bases are. All right. But the good news is, this is it. This is the last chapter. Is that something you thought I would be saying anytime soon? This is the last chapter. We're almost done with this. Hooray! All right. This is probably the most relevant chapter, I would say. Mostly because the notion of pH is something that's very important physiologically. If your blood pH is too high or too low, you will die very quickly. And your body has many mechanisms in place to prevent that from happening. One is your stomach. Anything that you eat goes through your stomach, which is really, really, really acidic. So eventually the pH of anything that you eat becomes the pH of your stomach. So if you've been buying that water that's like pH 9 or is very high pH and it's expensive, don't buy that shit. It doesn't do anything. Everything becomes pH 2 once it hits your stomach anyway. The next thing that it has to safeguard pH changes is what's called a buffer. And buffers resist changes in pHs chemically, and we'll talk about that at the end of the chapter. But in order to understand how all this biology works, we got to talk about the nitty-gritty details of what acids and bases are. So we're probably going to just do this first little section, and not even all of it. We'll talk about what an acid and a base are. So let's define these things. What are acids? Acids have these properties in common, and I just like using this picture of this girl going, You're going to see her again in a second. Acids taste sour, so you might have eaten some things like lemon. Lemon juice is an acid. It's citric acid. It's very sour. The tartness that comes from other citrus fruits, so like say an orange, or a lime, or a grapefruit, these are all different amounts of acids. If you've ever tasted vinegar by itself, it's super sour. It's like, oh, why did I do that? Ugh. I don't like vinegar that much myself. Acids have a property that they are very corrosive to metals. Metals dissolve very readily in acids because they undergo oxidation reduction reactions, which we briefly talked about in Chapter 9. But acids facilitate these things. There is a special paper out there called Litmus Paper, and the purpose of Litmus Paper is that it has a dye on it, and what the dye does is it changes color based on the pH. If something is acid or acidic, then when you expose litmus paper to it, it turns red. Later on, we're going to see that litmus paper exposed to a base turns blue. Finally, acids and bases neutralize each other because they are essentially functionally opposite. Where are acids found? Fruit. Some acids are used industrially, so we might use like sulfuric acid. We might use hydrochloric acid or nitric acid or phosphoric acid. Other places that acids are found are in different foods. Acids are quite common, and for the most part, depending on how much of the acid you are exposed to, they can be safe. For instance, you aren't going to get sick and die from eating too many lemons or too many oranges. If that were the case, that would be really sad because I really like oranges. Oranges are really good. I also like lemons and limes. I don't care for grapefruit, though. The acid in your stomach is HCl. All of that salt that you eat with the chloride part on it, the chloride kind of just ends up in your stomach. I mean, the chloride is important because it's negatively charged, so there is physiological use for it to maintain charge balance in your body. But a lot of it ends up in your stomach, and the proton pumps there are adding H plus to it, which is just where the acid is. Here's a bunch of different acids that are common. This is just sort of for your curiosity. You're free to read this on your own time if you'd like. But the ones that I think are the most important are probably, let's see here. What do I really care? I mean, they're all kind of important. I'm going to mention this one just because phosphoric acid is what gives Pepsi and Coca-Cola their tartness. So if you've had Pepsi or Coca-Cola and you taste it and there's like a little tang aftertaste, that's phosphoric acid. If you drink Sprite or 7-Up instead, you get a different aftertaste because they have citric acid instead of phosphoric acid. Citric acid is not as strong of an acid as phosphoric acid is, and so you get a different aftertaste. It's a little less sharp. The other one that's in beverages is this one. This is carbonated water. Carbonic acid is the combination of water and CO2. When you put CO2 into water, you make carbonic acid, which is a very weak acid. So if you drink just straight seltzer water or club soda, it has a kick to it, and that kick is the acidity. The last mention I'll make is hydrofluoric acid down here. Hydrofluoric acid is deadly. Don't touch it. Just stay away. That'll kill you very quickly. Alright. Here's some pictures of those molecules and their structure. Particularly, the important feature of an acid is this thing right here. So you'll notice that they all have this H in them that I'm highlighting. Sometimes when H is bonded to another atom, what will end up happening is that the bond will break and we'll end up with this and then a minus charge on the other thing. This is what's responsible for the acid, making H+. Now, not all H's do this. Particularly, very polar bonds cause H to fall off. Now, we learned that CH bonds are essentially nonpolar. So these bonds don't form H+. They hang out. The C and the H are buddies. But OH is a very polar bond. H is much less electronegative than O is. So whenever you see OHs connected together, depending on the other structure around, you might split them into these pieces, H+ and O-. Over here, the same thing happens, H+ and Cl-. In all these cases, we are making H+. Now, I want to draw particular attention to this group right here. This is what's known as a functional group in organic chemistry. If you see this group, C double bond O, OH, that H is acidic. And so this is called a carboxylic acid. If you're taking Chem 131, and if you're in the nursing program, I would recommend that you take Chem 131 because it's useful, then you're going to see carboxylic acids all the time. Carboxylic acids are important in things like fats. For example, lipids are formed by combining a carboxylic acid with glycerol. You can make amino acids, which are proteins, by combining a carboxylic acid with an amine. Amines are things with nitrogen in them. And so, whenever you see this group, you should think, oh, that H is going to fall off as H+. But whenever you just see C's and H's connected, those C's and H's just stay connected. They don't do anything, because they aren't polar enough. Alright, that's acids. Let's talk about bases. Bases have the following properties, which are kind of the opposite of acids. Now, the opposite of sour is not really something we can quantify. It turns out that it's bitter. There's that picture again that I just thought was appropriate. Bases are really bitter. If you've ever tasted pure caffeine, maybe like... so the example I give for this is a friend of mine in college had breath mints, and they had caffeine in them because our chemistry class was at 9 a.m., and I'm not a morning person by any means. That's why I'm teaching the night class. But we had to get up at 7:45 or whatever, go get food for breakfast, and then we had to go to chemistry. And of course, we were very tired, so he gave me these breath mints. I don't know if there was a reason that they were mints. Maybe my breath was really bad. I don't know. I brushed my teeth, but inside the breath mints was caffeine to wake you up. And I remember I ate one, and you taste like the sweetness of the breath mint, and then the aftertaste was this super, super bitter. Like, oh, what is that? And that was when I became a super taster for caffeine. So now whenever I taste anything with caffeine in it, I'm like, oh, yep, that's what that is. That lasted for like 20 years. Now I can actually go back and like drink Pepsi and be like, oh, okay, yeah, I don't just taste overwhelming caffeine. Many bases are like that. They're just very bitter. If you've had pure cocoa is very bitter. And the reason for that is it also contains caffeine. But there are other bases in that too. Bases tend to be slippery. The reason for this is because they dissolve your flesh. Just FYI, every time you use soap in the morning, soap is a base. Or in the afternoon. You can use soap whenever you want. Soap dissolves your flesh. Just in case you didn't know that. You don't need that layer of flesh. It's dead anyway. But what soap does is, in any base really, is it reacts with fatty acids, so lipids and things like that. And it causes them to undergo a process called saponification, which dissolves them. In other words, it breaks apart some of the bonds in them and makes a new substance. And that substance is just fatty acid chains, which are very slippery. If you feel your skin after you've used soap and water and it feels slippery, congratulations, that skin has been washed away. It has been dissolved. Like we said before with litmus paper turns bases blue. Or I'm sorry, bases turn litmus paper blue. And then finally, bases neutralize acids because they are the functional counterpart. Where do we see bases? Bases are very common in cleaning products, not so common in foods. The reason that bases are so bitter to our senses is because many bases, are toxic. In small quantities, these bases are okay. So like caffeine in coffee and dark chocolate is okay in small amounts, but you don't want tons of caffeine. Like if you consume large amounts of caffeine, that could be bad for you. But small amounts are okay. Just a little caffeine is fine. Most commonly, we see bases as cleaning products. So oven cleaner is a very common base. Lye is a very common base. Lye is actually used to make soap, for instance. You take animal fat and lye and you get soap. Yep, but yeah, the soap that you've been using is animal fat, by the way. Sorry to surprise you all, if you didn't know that. What else is common for base? Antacids. Antacids are important for health because sometimes you get an upset tummy, and then you need to neutralize the excess acid that is in your stomach, and you take an antacid to do that. What's actually happening is when you get an upset stomach, you are actually short on acid. You don't have enough, but your body doesn't make it fast enough because it doesn't think there's an emergency. So you take an antacid. At least this is my understanding. You take an antacid, and then it neutralizes a lot of the acid in your stomach, and your body goes, oh, holy shit, I need to make acid. And then you feel better. So antacids are important too. I think this is a list. Yeah, here's a list of a bunch of different acids that... I'm sorry, a bunch of bases. Oh, I forgot ammonia. Ammonia is also a base. Ammonia is basically Windex. If you have Windex in your household and you open it and you smell it, that really caustic smell that you smell is ammonia. Bases are really good at cleaning because most things that we need to clean are things like grease and dirt and grime and grit and stuff like that. And all of those are fatty sort of things. So we saponify them, and then they become soluble in water, and then you can wash them away. So that's really useful to us because we like our house and body and everything to be clean. That's really the gist of it. Alright, so that's what acids and bases are. Give me just a second. I'm going to peek ahead to see how much of this I can do. This is kind of an involved topic. I don't know if I want to start this with only 10 minutes left. So what I'm going to do is we'll end here. We'll call it a night. We'll end 10 minutes early. That seems good. I'd rather not cut off the discussion of how acids and bases are written in reactions midway, because that seems like a really confusing part to start back up again. But yeah, that's where we'll stop. On the note of this last thing that we talk about in the quarter will literally dissolve your skin. Anyway, thanks for watching. Sleep well and dream of bases.